Hello! So today we are going to talk about friction, and specifically in this video, kinetic friction. So friction always acts parallel to the surface of contact. So it's a sliding force basically. So it's going to act parallel to the surface, and since the normal is always perpendicular to the surface of contact, your friction is always going to be perpendicular to your normal, always, without exception. There's two kinds of friction, static and kinetic. Today we are going to talk about kinetic friction. So static, there's no relative motion of the surfaces, and kinetic, there is. It's sliding. So for kinetic friction, the magnitude of friction depends on only two things: the types of surfaces in contact and the size of the normal force. So let's look at this. We have a crate here. So we have a guy pushing a crate. So this crate right here. And then this jobby on top, we'll use to put different masses on top to change this normal force by the ground on the crate. So if the crate moves at a constant velocity, compare the horizontal forces. So we're not concerned with the vertical forces at this point. So we have the person pushing the crate, and then we have friction. Do you agree with this? I hope you said no. The key here is that it's moving at a constant velocity, right here, constant velocity. So if it's moving at a constant velocity, the crate and the floor should have the same magnitude. All right, so if we we could push the crate down towards the floor, which would make the normal force larger, or we could pretend that there's a string attached to the box. We could pull it up a little bit and make the normal force by the floor on the crate lighter right here. So we are in this thought experiment, we're pulling a cable to the right at a constant velocity. So this tension on the cable that we can measure is going to be equal to the friction. If we do this for several different times with the different pushing and pulling on the crate to change the normal force on the crate, we will get a graph similar to this. And of course, if we draw our best fit line through these points, which in our imaginary world, our points are perfect, our tension is going to be equal to our friction because we're moving at a constant velocity. And if we write the equation of the line, y is equal to mx plus b. In this case, y is our vertical, so that's our friction, equals the slope times the x, which is our normal force. And in our class, we'll use small n, although this is an old PowerPoint, we're going to use large N, by the ground on the crate, or whatever you're talking about, ground on crate. And in this case, our y-intercept is 0. So, the friction is constant, is a constant times the normal force, and we call this constant mu, or coefficient of friction. So mu k is a coefficient of kinetic friction, is a Greek letter mu. So if I cover the bottom of the block with sandpaper, you would expect the friction to become more, yes. So you'd want a greater friction up here. If we cover the bottom of the crate with like oil or some lubricant, the friction becomes less. So our mu, the coefficient of friction between the two surfaces, becomes smaller. All right. So the coefficient of friction is the symbol mu. It represents the roughness between the two surfaces. It must be measured or tabulated for any pair of surfaces. And it's just a number. It has no units. If we look here, if we look here, friction equals mu n. This has units of newtons. This has units of newtons, so this will be, the mu is unitless. Okay? So that concludes our video. All right.